Good morning, everyone. Today, we'll be discussing the rules for using symbols of SI units for measuring length and large distances such as the distances of a planet or star from Earth using the parallax method. Let's get started. Use of SI units follows strict rules. All symbols should be written as capital letters without intervening spaces, including punctuation, for example kilogram, m. S symbols must be accompanied by an appropriate SI prefix, for example kilogram, millimeter, m, or second, s. Symbols should not be used as fractions or decimals. When a unit is part of a compound, the symbol should be preceded by a full stop, for example m. S. It is essential to follow the standards for the symbols of SI units. Full unit names should be written in lowercase letters, but if the unit is named after a scientist, then the symbol should be represented by a capital letter. For instance, Newton should be displayed as N, watt as W, and ampere as A. The symbol for units should be used as singular, not plural 100 kilograms, not 100 k. G. 100 newtons as 100 N, not 100 Ns. Likewise, 50 meters should be written as 50 meters, not 50 milliseconds or 50 mts. Furthermore, punctuation marks should not be used after the symbol of a unit. Symbols for SI units should not be made plural, a punctuation mark should follow the symbol, and a small letter should be used when the symbol of the unit is placed after the name of the scientist. Length is a quantifiable size of an object's size. It is commonly gauged in feet, miles, centimeters, or meters. In industries such as construction and engineering, it is essential to be able to measure length accurately. The most common metric unit for length is the meter, which is equivalent to 100 centimeters, while the inch is the most popular American unit of length, wherein 1 inch is equivalent to 2.54 centimeters. For precision measurements, millimeters are often preferred since 1 millimeter is equivalent to 0.1 centimeters. Additionally, other units of length like leagues, fathoms, and yards are also employed for measuring longer distances. Measuring length is an essential part of life. We have a range of tools to accurately measure length, from the basic meter scale to the more sophisticated vernier calipers, screw gauges, and spherometers. These direct methods are capable of determining lengths from 10 to 3 meters to 10 to 5 meters with an accuracy of 10 to 4 meters to illustrate. One could use a meter scale to measure the length of a book. The parallax method is a key tool for measuring large distances, such as those of planets and stars from the Earth. This technique involves comparing the apparent change in position of an object when viewed by one eye from two different vantage points, allowing us to measure the distance between 2 points. This method has been used for centuries and remains an essential tool in aiding our understanding of the universe. Parallax is a phenomenon used to measure distance. It occurs when 2 points of observation are set apart, with the distance between them referred to as the basis. This basis is used to measure the distance, denoted as d, of a planet P located far away. To calculate this distance, 2 points on the Earth, A and B, situated at a distance AB equals B, are observed from. By measuring the distance of the planet from each of these 2 points, the distance of the planet can be determined. Parallactic angle is a method of measuring angles between two directions along which the planet is viewed at 2 points. An angle, however small, can be taken as an arc of length b at a circle with its center at P and distance d as its radius. This enables a calculation of the diameter and angular size of a planet based on the determined distance d. Among the concepts related to units and measurements, the ratio of the arc length to the radius of the circle is important. To understand this, one must consider two diametrically opposite points on a planet, viewed through a telescope from a point on the Earth. The angle between the two directions viewed is measured, and by taking into account the radius of the circle with the center at the observer, it is possible to determine the angular measure. This allows us to calculate the ratio of the arc length to the radius of the circle. Molecules are incredibly small and hard to measure even with the most powerful microscopes. But with the development of the tunneling microscope, it is now possible to determine the size of molecules, including oleic acid. To measure the size of oleic acid molecules, one should prepare a dilute solution in alcohol. After that, a technique that involves lycopodium powder spread over the surface of the water can be employed for estimating the size of the molecules. In scientific experiments, it is important to have an accurate understanding and measurement of units. For example, in this experiment, we have n drops of a solution with a volume of V being added to water, forming a thin, large, and circular film of molecular thickness on the surface. By measuring the diameter of this film, we can calculate its area. It is essential for each unit of measure to be precise, as even a slight error could result in an incorrect outcome. Our world is full of measurements and units of length that precisely define different lengths. Within the scope of the metric system, widely utilized, the range of lengths extends from nanometer, 1/1000th of a meter, to gigameter, 1 billion meters. Other systems such as the imperial system or the U.S. customary system can also be used, and most countries are adapting new standards, like the International System of Units. Being able to measure accurately and dependably is an essential part of our daily life. The range of lengths we encounter in our world is immense, spanning from 100 millionth of a meter to 10 billion meters. To measure these lengths, the metric system is typically used for smaller lengths, while astronomical units and light years are necessary for larger lengths. As our universe is incredibly large, these special length units are necessary for us to comprehend its enormity. We are examining units and measurements more closely. When discussing length, keep in mind that 1 Fermi is equal to 10 to the minus 15 meter, 1 angstrom is 10 to the minus 10 meter, and 1 astronomical unit is the average distance of the Sun from the Earth, 1.496 times 10 to the power of 11 meter. Another unit of length is 1 light year. The distance light travels in 1 year, 9.46 times 10 to the power of 15 meter, and 1 parsec is equal to 3.08 times 10 to the power of 16 meter, which is equal to the distance at which the average radius of the Earth's orbit subtends an angle of 1 arc-second. When discussing an object or measuring the distance between them, we must take into account the lengths on various scales, from incredibly small to visible. Meters are the common unit used to measure length. A proton is approximately 10 to the power of minus 15 meters, the size of an atomic nucleus is about 10 to the power of minus 14 meters, the size of a hydrogen atom is around 10 to the power of minus 10 meters, and a virus is around 10 to the power of minus 8 meters, while the wavelength of light is 10 to the power of minus 7 meters. At the large end of the scale, the size of a red blood corpuscle is approximately 10 to the power of minus 5 meters. To properly deal with objects and measure length, it is important to understand the range and hierarchy of these lengths. Measuring distances and lengths is critical as we delve deeper into the universe. This example demonstrates the various lengths that need to be measured, from the thickness of a sheet of paper to the distance of Pluto from the Sun, in order to have an accurate assessment of any astrophysical occurrence. This system of measurement allows us to accurately quantify the size and distance of any given object or phenomenon. It is amazing that objects and distances can be measured with the unit of a meter. A meter is approximately equal to the length of a yardstick. We usually measure areas and volumes with different units, but meters are typically used to measure the distance between 2 points. For example, the size of our galaxy is about 1021 meters and the distance to the Andromeda galaxy is estimated to be 1022 meters. Moreover, the boundary of the visible universe is estimated to be an astonishing 1026 meters away. Mass is a fundamental physical quantity which has an inherent property. In the International System of Units, SI, the primary unit of mass is the kilogram, yet other measurements can be utilized, such as the gram, pound, or ton. Assessing mass is done utilizing a balance or dynamometer. Mass is an intrinsic characteristic of matter, unaffected by temperature, pressure, or spatial coordinates. It is quantified using measure units such as kilograms, grams, and milligrams, which are essential to comprehending the behaviors of matter and its reactions to environmental forces. Consistent and accurate measurements are hence indispensable in analysis of matter's characteristics and force impact. The kilogram is the SI unit of mass, originally defined by the prototypes of the International Bureau of Weights and Measures. These prototypes can be found in laboratories all around the globe, National Physical Laboratory in New Delhi being one for India. The kilogram provides us an effective and precise way to measure mass in any region of the world. Unified atomic mass unit is a unit of measurement used for the mass of atoms and molecules. Its size is extremely small, and it is equal to 1.66 times 10 to the minus 27 kilograms. Having this unit makes it much simpler to measure mass on an atomic scale. With it, we are able to gain an accurate representation of the mass of atoms and molecules. Gravitational method of measuring large masses like stars and planets relies on Newton's law of gravitation. For arbitrary objects, a balance is employed. For atoms and subatomic particles, mass spectrograph comes into play. This device measures masses of charged particles by using electric and magnetic fields, with the particle's trajectory radius proportional to the mass. Objects have a mass, which is a way to measure the amount of matter it contains. The range of masses, from the electron to the uranium atom, is huge as it covers 27 different orders of magnitude. Each object, from raindrops and dust particles to blood cells, will have a mass within this range. Knowing how to measure and compare the mass of various objects is a very important part of studying the universe. When it comes to scientific measurements, the scale of objects can range greatly. A mosquito's mass is approximately 10 to the power of -5 kilograms, while a Boeing 747 aircraft is roughly 10 to the power of 8 kilograms. An understanding of the mass of an object must be considered when making measurements, as the range of masses can range from 10 to the power of -5 up to 10 to the power of 23. We can clearly see from the numbers that the mass of Earth is 10 kilograms, Sun 25 kilograms, Milky Way galaxy 10 to the 30th kilogram and observable universe 10 to the 41th kilogram. Despite their large differences in size and mass, they all have the same measure in mass. It is truly remarkable. The correct answer to this question is D, all of the above. Mass can be measured in units such as the unified atomic mass unit, the kilogram, and the gram, meaning that all of these units are units of mass. Measuring time has been with us since ancient times. Various methods to measure time have been developed, including sundials, hourglasses, and modern atomic clocks. In this lesson, we will look at the different units and measurements used for measuring passing of time. Time is an essential component of modern life, and the most accurate way of measuring it is through the cesium atomic clock. This clock bases 1 second on 9,192,631,770 electromagnetic oscillations corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. Thanks to the precision of the atomic standard, we now have the ability to measure time intervals with unprecedented accuracy. In many countries, the cesium clock, also known as an atomic clock, is used as the national standard. Atomic clocks are highly effective and accurate for calculating and staying on track of time intervals. Cesium atomic clocks are particularly efficient, as their precision extends to 1 part in 10 trillion. They are used as the standard guideline for making sure frequencies and time intervals are up to date, and in India, Indian Standard Time is connected to this set of atomic clocks. Consequently, cesium atomic clocks are an invaluable source for accurate frequency and time interval measurement. We will explore different units and measurements of time, such as intervals in seconds, period of radio waves, sound waves, the wink of an eye, the time between human heartbeats, and the travel time for light from the moon to the Earth and also from the sun to the Earth. Let us observe how these different measurements of time differ. Units and measurements are the focus of this slide. 30 different events are used to illustrate the time interval. A satellite's time period is 10 seconds. The Earth's rotation period is 5 seconds and the Moon's revolution period is 10 seconds. Additionally, 6 seconds is the time it takes for light to travel from the nearest star. To conclude, humans typically have a lifespan of 10 seconds. We can observe from the data that time sprawls across a vast range of lengths. The time intervals range from 10 seconds to 17 million years. For instance, the Egyptian pyramids are speculated to be around 4,500 years old, whereas the universe is estimated to be 13.7 billion years old. These are just some of the different measurements of time.